Properties of logarithms. So in the previous section, we learned that logarithms are actually exponents. So we're going to rely on properties of exponents to derive the laws of logarithms. Let's take a look at the first properties, the first list of properties. Here's the setting. You have a number a that's positive and different than 1, that's going to play the role of a base, and three numbers a, b, c, where a and b are positive. So these are going to play the role of the argument, the input in the log base a function. Then the following holds. Property 1, the log of a product is equal to the sum of the logs of the factors, right? A and b are the factors here. Property 2, the log of a quotient is equal to the difference of the log of the numerator and the log of the denominator. A being the numerator and b being the denominator, right? And the last property, property 3, the log of an exponential expression with base a and power c is equal to that c times the log of the base a, capital A. Okay? All right, so as I told you here at the beginning, we're gonna rely on the laws of exponents to actually derive the laws of logs. You're gonna see that in the proof of all three of these. Okay, let's show each one of them. So let's show the first one. We want to show that log base a of a product is equal to the sum of the logs of the factors. Okay, so we're trying to show part 1. Let's give this guy a name. Let's call this guy, let's say u. Log base a of a. And how about v for a name for this guy? And let v be log base a of b. Okay? What does this mean? What does this mean? Let me try again. What does this mean? Well, if u is the log base a of a, this means that, again, based on the definition of logs, previous section, this is the same thing as saying what? This means that a to power u is equal to a, right? This is the definition of this is the definition of logs, and this writing we used to call it the equation in log form, and this is the equation in exponential form, right? All right, so and they are equivalent. So u equals log base a of capital A is the same thing as saying that the base raised to power u is equal to a, by definition, right? Let me just put the emphasis here. This is just the definition. How about the next one? How about this one? Well, same thing applies, right? Also definition. That's the same thing as saying a to power v is equal to b, right? All right. And how about now we try to write the left-hand side. Remember, I'm trying to show part 1. Let's take a look at the left-hand side. Log base a of capital A times b. Let me write that. So then, the left-hand side, which is log base a of capital A times b, right? This is the left-hand side. This is equal to log base a. And what is capital A? It's little a to power u, right? It's little a to power u. And what's capital B? It's little a to power v. So capital A times capital B becomes little a to power u times little a to power v. Make sense? Okay. And look here. The base is positive. AU times AV. You are multiplying two exponential expressions. I'm talking about this guy, right? You are multiplying two exponential expression with the same base. So what do? We keep the base and we add the powers. So we keep the base and we add the powers, right? Make sense? All right. And then what is this guy? Log base a of a to this power. Ignore this guy for a second. Just ignore this guy for a second. This is log base a of ax. Well, log base a of ax is simply x, remember? Because log base a back to back with the exponential function with base a, previous section, they undo each other's action, and whatever sits here is going to be the output, right? So this is simply u plus v in this case, right? One more time, log base a back to back with the exponential function with base a, back to back, no action, neutral action. So the output is simply this guy, whoever sits here, it happens to be u plus v. And who's u? U is log base a of capital A. So this is log base a of capital A. And who's v? Who's v? V is log base a of capital B. Right? And now take a look. Take a look here. This guy, log base a of the product AB, which is the left-hand side of the property I'm trying to show, we showed it, I mean, they're all equal to this guy. And what's this guy? This is the right-hand side that I wanted to get to. So we've just shown that log base a of a product is the sum of the logs, right, of the factors. So part one is complete. We showed it. Part two. We want to show now that the log of a quotient is equal to log the difference of the log of the numerator and the log of the denominator. Well, we can play the same game. We can play the same game that we just played here. Let me highlight what the main difference would be. Instead of product, it's going to be division, right? So instead of this, it's going to be a division. Am I correct? This would be for part two. I'm trying to, since I have a blueprint now, I'm trying to actually use that to derive property 2. If you change this guy to division with the same setting, then this is going to be division, right? So then this is going to be division. And what's AU divided by AV? What's AU divided by AV? Taking the quotient of two exponential expressions with the same base. What do? You keep the base and you take the difference of the powers, right? The first one being the exponent of the numerator. So this would translate into a minus here. Correct? Because you're taking the quotient, AU divided by AV would be the quotient of two exponential expressions. As such, the exponents, the division translates at the level of exponents to a minus, right? And this minus forces this to become a minus. It's the same one. And then this is going to be a minus. And hence, look, log base a of a divided by b, which is the left-hand side of part 2, is ultimately equal to log base a of a, the numerator, minus, right, minus log base a of the denominator. So property 2 is already shown by the same proof. Make sense? Let me show you a different proof for part 2. Even though you believe that part 2 is true now, right? Because we just showed it. Let me show you a different proof for part 2 that uses actually part 1. Okay? So for part 2, let me write log base a of, how about I start writing, let me just see here, how about I just writing log base a of a as log base a of a over b times b. First, do you agree that this is correct? what I've done here is I simply rewrote A as A divided by B times B. This is the same thing as A, right? B divided by B is still 1, so this whole thing is A. So I haven't changed the value of this argument. This is still A. Okay? All right. And now part 1 tells me that the log of a product, ignore the letters for a moment, A, B, forget about letters A, B. The log of a product is equal to the sum of the logs of the factors. Well, I'm going to apply part 1 where this is one of the factors and that's the next one, that's the other. Correct? So I'm going to use part 1 now. I'm going to use part 1 here. How about I highlight them for you? This is one of the factors and this is the other. Okay? So as such, I get this equal to log base A of the first factor plus log base A of the second factor, which is B. Correct? One more time. Log of a product is the sum of the logs of the factors. One of the factors is A over B, the other one is B. Correct? This is part 1, because part 1 now is correct. I mean, at this point here, part 1 is correct because we showed it. Now I can use it. I'm using it in part 2. Very good. And now look at this. So what have we shown? We've shown that this guy is equal to this guy, right? So let me write it. We've shown that this is the case. And what do we want? We want that this guy is equal to log base A of capital A minus log base A of capital B. So it suffices now to subtract log base A of capital B from both sides to get what we want, right? So subtracting log base A of capital B from both sides yields what? It yields the following. Log base A of capital A minus log base A of capital B is equal to log base A of A over B, right? That's what we get. One more time, what did we do at the end? So we established this equality, we established this identity over here, and then we subtracted by this amount log base A of B from both sides. So it's going to disappear from here, it's going to pop up on this side with a minus sign. That's what's going to happen. Agree with me? Okay. And now, isn't that what we wanted? Isn't that part 2? I mean, take a look. This is not part 2. That's not what we want. It's exactly the same, written backwards. If something is equal to something else, then the latter is equal to the former, right? So equality is reflexive in some sense, right? X equals y is the same thing as saying that y is equal to x. So we're done. We showed part 2. Part 3, log base A of capital A to power C is equal to C. That power now comes down as a coefficient times log base A of the base. Okay, so let's show that. Okay, this is part 3. Let's start as we started in part 1. Let's call U to be log base A of capital A. And what does this mean? This means, or this is equivalent to say that A to power U is equal to capital A, right? Okay. So then, what can you say about the left-hand side of property 3, which is log base A of capital A to power C? Well, that's the same thing as who's A? Who's capital A? It's little a to power U, right? It's little a to power u. Correct? So that's the left-hand side of property 3. I'm unraveling what it means. Well, capital A is little a to power u to power c, right? So we get this setup. And there is a positive thing, positive base. So here you're raising an exponential expression to a certain power. Then you keep the base and you multiply the powers. This is one of the rules for exponents, right? I hope you get to see, I hope you are realizing that what we're using to prove all of these are actually the laws of exponents, as promised. So we get a to power u times c, right? Correct? So you keep the base, you multiply the powers, u times c. All right, here one more time, log base a back to back with the exponential expression with base exponential function with base a. So back to back, neutral action, we only get u times c, right? We get u times c. And what's u? What's u? It's log base a of capital A. So u times c is the same as c times u, and u is this guy, right? So this is the same thing as saying c times log base a of capital A, right? Right? Because that's u. U times c is the same thing as c times u. And now look, log base a of capital A to power c is equal to c times log base a of capital A. That's exactly property 3. That's exactly what you wanted to show, property 3, right? So you see, as I said, I mean, since logs are exponent, we're gonna rely on the laws of exponents to derive the laws of logs. And look, and for property 1, which property of exponents we used? You see it? It's right there. It's right there. We are multiplying two exponential expressions. We add the powers. For part B, which one did we use? So for part B, for part 2, we showed it in 2 ways. One of the ways was we used the division of two exponential expressions with the same base. So we chip away the exponent of the denominator from the exponent in the numerator, right? This is one of the laws of exponents. And for the last one, for property 3, what was the property that we used? It's right there in this step. We multiply those powers, right? We kept the base and we multiply the powers. So you see how the laws of exponents, because log is an exponent, right? So you see how the laws of exponents actually imply the laws of the logs listed as properties 1 through 3 here. Okay. All right, let's put these in action. Let's go to the book. This is section 3.4, page 404. And let's go to, let's do one of these from 7 to 12. Let's see the question. Use the product property of logs, so it's property labeled 1 in our discussion. So the product property of logs to write the log as a sum of logarithms, then simplify it if possible. Okay, so we have a log of one thing and we want to try to use the product property of logarithms to kind of expand it, right? Write it as a sum of logs. All right, let's say the last one, 12. Log base 3 of a plus b times c. Okay, this is number 12. So this is on page 404, number 12. So remember the question? We have log base 3 of a plus b as one of the factors times c, correct? And what's the question? The question is we want to write this as the log as is, this condensed log as a sum of logs, right? Using the product the product property. Okay, so we're gonna use that product property, which is labeled here as property 1, right? And that property, if you remember, what does it do? This is what property 1 is, right? It takes the product, so logs splits the product as the sum of logs, right? Okay, so what's the product here? The product here is a plus b as one of the factors and c as the other one, right? And c as the other one. So I'm highlighting these factors for you. So property 1 then tells us, well, this is log base 3 of one of the factors, so a plus b, plus log base 3 of c, right? Okay. And can we do anything else? Well, this is a log of a sum. Log of a sum. Let's go to the list of properties we have. Do you see anywhere log of a sum? The only place I see sum is here. This is not the log of a sum. This is a sum of the logs, right? This is a sum of logs. But what I have below is, instead of this, a plus. And I see nowhere a property to this end. So I don't have anything at my disposal to actually use. And as a matter of fact, there's no formula for to split the log over addition. Okay. All right, so this is the best we can do. We wrote it as a sum of logs. That's it. All right, back to the book. Okay. Similar story for this, but now we're going to use the quotient property. Let's stick with the last one here as well. How about this? 18. Log of a quotient where the numerator is 1000, downstairs is c squared plus 1. So this is number 18. So we have log of 1000 divided by c squared plus 1. By the way, whenever we don't have a base, whenever we don't write the base, the assumption is that the base is 10, right? This is the notation of log without a base. The base is there, but we don't write it. And this is the common log function, right? This is the name of such a function, log base 10. All right. Very good. So this is property 2 is going to handle it, because property 2, if you remember, is log of a quotient. And the log of a quotient is the difference of the logs. Difference of the log of the numerator and the log of the denominator. Okay. Who's the numerator here? Is 1000. So property 2 tells us this is log base 10 of 1000 minus log base 10 of c squared plus 1, right? Remember what we just said? Log doesn't split a sum, right? There's no formula for log acting on a sum. There is a formula for log acting on a product, right? And log acting on a quotient, log acting on an exponential expression, but there's no formula for log acting on a sum. So this expression is, it is what it is, so we cannot change it. Okay. Now this guy over here, log base 10, remember this is the base 10 of 1000. Well, 1000 is 10 cubed, right? 1000 is 10 cubed. So that's the same thing as log base 10 of 10 cubed minus log c2 plus 1. And what is this? Remember here the base is 10. The base here is 10. So let me write it for you just to be there. So it's a 10. So look, log base a of ax. Log base a back to back with the exponential function with base 10 back to back. Neutral action, the outcome is only that exponent, right? So what's that then? This is a 3 minus log base 10 of c2 plus 1. Yes? So I'm gonna erase this 10 for you now. Okay. All right, sounds good. And that's the best I can do. Okay, as we said, log of a sum, we can't do anything about it. All right, back to the book. How about now for problems from 19 to 24? Let's choose one of these. How about the last one, 24? The question is apply the power property of logs. Power property is our property 3. Okay, so we have ln. Remember ln? ln is log base e, natural log function. ln of 0.5 to power rt. Okay, so this is 24. ln of 0.5 to power r times t. Okay. So this format here is of the form a base, which is positive, to some power, right? Whatever this power is. So property 3 in the list of properties we just proved, this one, property 3. Base a is, I mean, not the base, the base of the log, right? The function. That thing over there in problem 24 is e, the base e, right? Euler number. And this base, capital A, in our case is 0.5, and c in our case is r times t, right? So that's going to be r times t times log base e, so ln of 0.5. Okay, all right. So then by property 3 over here, that's going to be the exponent rt times log base a, so ln in this case, of 0.5, right? So technically this power just goes down as a coefficient. Okay, very good. Quick comment here. Quick comment, let me change color. How about this? How about ln of 0.5 to power rt, like this, with this format? Okay, I included here brackets for, as part of the decoration, but they're gonna translate to something. What does this mean? How does the red part differ from this purple thing? Well, here the 0.5 is raised to power rt. Over here, it's the entire ln of 0.5 that's raised to power rt. Correct? So one more time, over here, it's the 0.5 that's raised to power rt, and as such, I can play the game of property 3. Over here, that's different. This is ln of 0.5, the whole thing is raised to power rt, and that's not this guy. That's not this guy, correct? You can take particular cases for r and t to show it, but I'm gonna just say, just highlight that they're not the same. Okay, so make sure that the guy inside the ln, the exponent, occurs to the base of the argument in the log function so that you can take it down as a coefficient, right? For this, that's not the same as this. Okay. All right. All right, back to the book. So now the next set, write the logarithm as a sum or difference of logs. Simplify each term as much as possible. Okay. How about we choose, how about 36? So this is ln of the fourth root of pq, p times q, divided by t cubed times m. Okay, so this is number 36. We have ln, which means log base e, of the fourth root of pq, p times q, divided by t cubed times m. Okay. All right, so what's the question? The question is to write the log as a sum or difference of logs. So we want to expand this expression. We want to expand. It's a condensed one, right? We want to expand it. Okay. Well, what's the structure here? ln is acting on what? What's the nature of this guy? It's a quotient, right? So ln is acting on a quotient. Do we know a property that handles such a thing? ln log acting on a quotient? Yes, it's property 2 above. It's property 2 above. So it tells us that it's the log, well, the log here is a natural log, of the numerator, right, minus the log of the denominator. Agree with this? Remember, we want to expand as much as we can. All right, now, what's the nature of this guy? Well, remember fourth root? Fourth root means power 1/4, right? Whenever it makes sense, this means power 1/4, or this is not denoted by this. It's a notation, minus ln of t cubed times n. All right, for this guy, what's the nature of the argument of ln? So ln is acting on what? It's acting on this. What's the nature of this? Is something raised to a power. Something raised to a power. So property 3 above tells us that this 1/4 can go down as a coefficient, right? So I'm going to use property 3 above to actually, bring down this 1/4, and then I'm going to get this, right? So this is property 3 above. So the 1/4 goes down times ln of pq minus this piece. Correct? All right, now ln over here, ln is acting on a product. This is p times q. ln is acting on a product. Property 1 tells us ln of a product is the sum of the ln's, or log acting on a product is the sum of the logs. So we get 1/4, this is by property 1 this time, times log of p plus log of q, right? And the log is a natural log in this case. So this is ln of p plus ln of q, right? This is by property 1. Over here, this is ln acting on what? It's acting on this times this. So it's a product still. So this is also a product. So this is, property 1 is still applicable, right? Log base a of capital A times capital B is equal to the sum of the logs of the factors. So it's minus the sum of the logs. So ln of t cubed plus ln of m, right? This is also part 1. So if you want part 1 times 2 twice. Okay. All right. We're gonna keep expanding as much as we can. We're almost there, almost there. So this means if you distribute the multiplication over addition, you get 1 over 4 ln of p plus 1 over 4 ln of q, right? Minus ln of t cubed plus minus ln of m. I can still expand this guy by property 3. It allows me to take this power 3 all the way to the level of coefficient, right? So by property 3, and this would be the last step here, we can bring down that power 3. We can bring down that power 3 and obtain minus 3 ln of t minus ln m. That's the last two expressions, right? Makes sense? Okay. Next. So this was 36. Which one should I do? Should I do 38? Let's do 38. So it's ln, same question. I want to expand this log. Ln of this fifth root of e squared divided by c squared plus 5. Okay. So this is 38. So I have ln of the fifth root of e squared divided by c squared plus 5, right? E is a number, it's a pure constant. C is a variable here, or a parameter, right? So don't confuse the two. E is not a variable in this context. Okay, E is a pure constant, it's known. It's like pi, okay, square root of 2 or something. E is approximately 2.718 as discussed in the previous lecture. All right. So I want to expand. What's the nature of the argument in the log function, the natural log function? It looks like the log is acting on the fifth power of that guy, right? So the nature of the argument is that thing raised to power 1 over 5, right? So this is the same thing as ln of e squared divided by c squared plus 5. And what I'm asking is, in some sense, what is the last operation taking place before ln takes place? Well, the last operation that's taking place before the log function is the 1/5 power. So this is then of the form something to power c, right? So property 3, the power property, tells us, well, you can bring down that 1 over 5, right? Property 3. So 1 over 5 times ln of e squared divided by c squared plus 5. Makes sense? So bring it down by property 3. This is the capital C in property 3. Bring it down and it sits here, right? As a multiplicative constant. This is a multiplication here. Okay. All right, now still, what's the last operation taking place within the ln? Or right before the ln takes action? Well, ln, the last operation taking place is the quotient, right? It's the division. And then ln takes place. So the structure now is log acting on a quotient. And log acting on a quotient is the difference of the logs by property 2. By property 2, right? So that the 1 over 5 is still outside, still sitting outside, times by property 2 is the log of the numerator minus the log of the denominator. And who's the denominator? C squared plus 5. I cannot simplify this, remember? Log doesn't split in any fashion over addition. There's no formula to that end. Okay. All right. How about this? How about this guy? Ln of e squared. Ln is the same as log base e, correct? Ln is the same thing as log base e. So that's the same thing as log base e. And what's log base a x? Back to back log base a with the exponential function base, the same base. They cancel each other, they undo each other, and then the output is simply x. And in this case, x is 2, right? So we get, oops, go back to purple. So this is 1 over 5 times 2. This is 2, right? Minus ln of c squared plus 5. Correct? Okay, and if you want to distribute the multiplication over subtraction here, you get 2 over 5 minus 1 over 5 ln of c2 plus 5. Correct? Okay. Let's keep going. All right, so it's the same thing over and over. Now let's play the game backwards. What have we done in these problems? In this set, the last couple problems, we expanded, right? So they gave us a condensed version of an expression and we expanded it. Over here, we're gonna go backwards. They're gonna give us an expanded version and we're gonna condense it. Make sense? That's the next. They wanna write the whole thing as a single log, right? So write the logarithmic expression as a single log with a coefficient 1. So the coefficient 1. And simplify as much as possible. By coefficient 1, they mean if you actually have to do, look, if the coefficient is not 1, just bring it as an exponent and get the 1, right? And get the 1. Makes sense? So this is what they mean. All right. So back to the book. Let's choose a problem. Let's choose a couple. Let's do 58. Looks a little long. 58. So 2 times the quantity log base 10 of p minus 4 minus log base 10 of p minus 1 minus log base 10 of p plus 4. Let's see. So 58. So 58 is 2 times log base 10 of p minus 4 minus log base 10 of p minus 1 minus log base 10 of p plus 4. And what's the idea here? We want to condense that thing. Okay. All right. Let's keep the 2 and try to condense the guys inside first. How about we start with these two? How about I mean, it doesn't matter. You can start with whichever you want, but how about we start condensing these two guys? So let's keep this guy by itself for the moment. So minus log base 10 of p plus 4. Let's not touch this for the moment. And let's condense these two. Well, this is a difference. This is a difference of 2 logs, right? With the same base, 10, correct? Property 2 tells us that this is the same thing as the log of the quotient p minus 4 over p minus 1. Correct? Property 2. So log base 10 of p minus 4 divided by p minus 1, right, is the same as this. If you're more accustomed to go backwards, I mean the backward direction, try to go backwards mentally. Log of this quotient is log of the numerator minus log of the denominator. So this is exactly this. Okay, and then this is log of something minus log of something else, right? So log of this minus log of that, right? So property 2 again, that's going to play the role of the numerator. This whole green thing highlighted in green is going to play the role of the numerator, and that's going to play the role of the denominator, right? So property 2 tells you then it's going to be 2 times log of the quotient that's made up from the numerator p over 4 over p minus 1 and the denominator p plus 4. Correct? Agree with me? And this is what? And this is what? How about we take this by itself and try to kind of like rewrite it or remodel it a little bit. This is the same as p minus 4 over p minus 1 divided by p plus 4, right? And dividing by something means multiplying by the reciprocal of the thing, multiplying by the reciprocal of p plus 4, which means 1 over p plus 4, correct? And this is then the same as you're multiplying two quotients. How do you multiply two quotients? Straight across, right? It's the denominator of the product between the numerator. So it's a quotient between the product of the numerators and the product of the denominators. P minus 1 times 1 is p minus 4 times 1 is p minus 4, right? And p minus 1 times p plus 4 is p minus 1 times p plus 4. Okay, so this bubble is exactly this. Okay, so and then what do we get? We get 2 times log base 10 still of the quotient p minus 4 divided by p minus 1 times p plus 4. Correct? Did we answer the question? The answer is no, and the reason is we haven't made the coefficient 1 up to this point, right? Let me take you back to the question. The question is, you want to write it as a single log. We did. This is a single log, but you want the coefficient to be 1, and what's the coefficient now? Is 2, right? But we already talked how to deal with this, how to make that coefficient 1. Just take that coefficient as an exponent because log allows you to do so, right? This is property 3. This is property 3. So property 3 then kicks in and allows me to rewrite this as a single log with 1 as a coefficient. And what do I get here? The square of what I used to have. So what I used to have is p minus 4, and downstairs p minus 1 times p plus 4. Okay. If you wanna foil this, be my guest, but there's no reason to do so. Okay. All right. Something else. How about 68? How about 68? Log base 10 still of 9t cubed minus 5t plus log base 10 of t to power negative 1. So 68. Log base 10 of 9t cubed minus 5t plus log base 10 of t to power negative 1, right? Okay. This is equal to what? This is a sum. This is a sum between two logs with the same base. The same as the base is 10. So by property 1, that's the same as log base 10 of the product, 9t cubed minus 5t times t to power negative 1. Agree? Okay. And then can we simplify this argument here? I mean, we wrote it as a log of a single log with a coefficient 1, but I feel we can still simplify this argument here. How about we distribute to see it better? How about we distribute the multiplication over subtraction? We get log base 10 of 9t cubed times t to the power negative 1 minus 5t times t to the power negative 1. Correct? And take a look here. Take a look at this. That's the same base with You're multiplying two exponential expressions here with the same base. You keep the base and you add the power. So this becomes t to the power 3 plus the other one, which is negative 1. Now what's 3 plus negative 1? It's 2, right? And how about this guy? How about this guy? This is same technique. So you keep the base, you add the powers, but this time around the sum of the powers is 0, and t to the power 0 is 1. Correct? T to the power 0 is 1. T in this, I mean, any non-zero entity raised to power 0 is 1, right? Any non-zero entity raised to power 0 is 1. You're going to tell me, how do you know that t is not 0? This would be a very good question. Well, the t is not 0 because, look, t to the power negative 1 means 1 over t, right? T to the power negative 1 means 1 over t. So this guy here is the same thing as 1 over t, right? And if t is 0, this whole thing doesn't make sense anymore. So all along, t is not 0. Also, on the other hand, if t is 0, look, this whole thing becomes 0, right? 9 times t cubed minus 5t. If t is 0, this whole thing is 0. As such, this whole thing here becomes log of 0. And log of 0 doesn't make sense. Because remember, log doesn't operate on numbers that are 0 or less. It only operates on positive inputs. So certainly t cannot be 0, and as such, t to the power 0 is 1. Any non-zero base to power 0 is 1. Okay? All right. And then finally, let's write the final thing. This is log of 90 squared minus 5. Correct? So we condensed to a single log with coefficient 1. Before we move on, let me ask you to think about this. So a little exercise. So how about this? ln of 1 over a. So show that this is equal to minus log ln, say, of a, and this is for any a positive, right? So let's try to show that these are the same. So we want to show this, right? So the left-hand side, which is ln of 1 over a, is equal to, by property 2, this is ln of 1 minus ln of a, because this is a quotient, right? 1 over a is a quotient. So by property 2, this is ln of 1 minus ln of a. And what's ln of 1? What's ln of 1? Well, log base a of 1 is 0. Remember that? Previous section. This is 0. So this becomes 0 minus ln of a, which is obviously minus ln of a as wanted, right? Okay. This came to mind just because of this, correct? I mean, as it happens, this is also the same as, this last one is trivial. As it happens, this is also the same as ln of a to power negative 1, right? The last one is trivial. Just take the last, 1 over a is a to power negative 1, am I correct? So since it was already equal to this, so all of these are the same. So it came to mind just because of this guy, okay? So you could have taken this minus here, or you could have written it as 1 over t, and so on, okay? So this is a useful thing to keep in mind. This is why I isolated it. All right, let's keep going. Here's a question. Let a and b be positive real numbers such that a is not 1 and b is not 1. And suppose that we have log base a we know the value of log base a acting on an input x, where x is positive. How do we find log base b acting at the same input x? So if you know log base a acting on an input, how do we actually kind of like transition to another base b and find the value of log base b of that argument x? Take a look at your calculator, your phone, let's say. Just go to your phone and open the calculator app and see that they don't have log base. They don't allow you to choose the base, right? The only thing that you see on a calculator are two things, either ln or log. These are the only two things you see on a calculator. So ln is the log base e, and log means log base 10. So if you want to find log base, 3 of something, you don't have a tool for it on a calculator. And the reason is there is a way to transition from one base to the next. This is actually this question. There is a reason to transition from a base to the next. So we can transition from the base 3 to either this or that. And these guys can be found on the calculator, right? This is the idea. This is why they don't allow you to cheat. Typically a calculator doesn't allow you to choose the base, because you can transition between one base to the next, okay? All right, so how can we handle this? Okay, how can we do it? How about we call that guy that we want something? How about we call it y? Okay, what does this mean? Well, this means b to power y. This is only definition here. B, right? That's the base to which you should. That's the exponent to which you should raise b to obtain x, right? So this is this by definition. All right. How about we apply log base a to both sides? If you apply log base a to both sides, log base a is a function, right? So for a given input, you get a unique output. So that's the same as this. If you apply log base a here, that's the same as log base a here, right? It's the same guy. Makes sense? I applied the log base a function to both sides. If a is equal to b, then f of a is gonna equal to f of b, right? The function f is log base a. So we get this, right? All right, property 3 just that we've been dealing with above allows us to bring this power all the way to the level of the coefficient, right? So by property 3, by the way, they're all equivalent. By property 3, we can write y times log base a of b equals log base a of x. Am I correct? We got this. And finally, remember, I'm trying to solve for log base b of x if I know log base a of x, right? So on a calculator, if you want to go to, let's say that a is like 10 or e, if the calculator allows you to find log base a of anything, how do we find the log base b of something? Well, this is what we're doing. We started with labeling this guy that we want to find as y, and as such we got to this point. Remember, this y that you see here, that's this guy, right? Okay, so I'm solving for this. I would like to know what this guy is in terms of log base a. And look at the other terms in this equation. You see this term here? This is an a, base a, log base a, and this is log base a, right? So far it looks good. To solve for y, now it suffices to divide by this entity. It suffices to divide by this entity. So it suffices to divide by what? By log base a of b, right? By this guy. And this guy is gonna remain here. Correct? So y times something is equal to this. Divide through by this thing, you get y by itself, right? And that's gonna be the numerator divided by this as a denominator. With one caveat, with one caveat here. And that caveat is what? I cannot divide by 0, right? I want to make sure that this guy is not 0 because I divided with it. I want to make sure that this guy is not 0. The question then is, when is log base a 0? The function log base a. Remember the function log base a? It used to have two trends. Either this, if the base is bigger than 1, right? Or that, if the base is between 0 and 1. Am I correct? And do you remember where both of these cross the x-axis? At 1, right? If you remember that. So at 1, the log function crosses the x-axis. And it's a function that's a one-to-one function. It's a monotonic function, I should say. It's a monotonic function. The only time it crosses the x-axis, which means the only time it outputs the value 0 is when the input is 1, right? The only time log base a of x, regardless what the base is, outputs 0 as an output, right? Outputs 0 is when the input is 1. Look at the pictures. So the only time then this is 0 is when b is 1, right? So the only time this guy is 0 is when, because I don't want this to be 0, I'm dividing by it. I want to make sure it's not 0. The only time this guy is 0 is when b is 1. But what do we know about b? Alright, thank God b is not 1. Right? b is not 1. So I can divide by this. So I can divide because b is not 1. Which forces this block not to be 0. So I can divide by this, right? Alright. And what's y again? Y is this. Y is this. So then we get log base b of x, right? This is the y guy. Log base b of x. Let me write the last step. So then we get y is equal to log, oh sorry, not y. I meant to write what y is. What's y? Y is log base b of x. So log base b of x is equal to log base a of x divided by log base a of b, right? So this is the change of base formula, the next formula. This is the proof of it. And this is true for any x being positive, right? So I recorded this over here. Why this is useful, as I said? For instance, in the calculator, you don't have log base 3. You only have ln which means log base e, or log, which means log base 10. So if you want to find log base 3, let's say, well, if you want to find log base 3, choose a to be either the 10 or the e, and then use the calculator for this side to actually deduce this side, right? So let me say I want to find on the calculator log base 3 of, I don't know, some number 7, let's say. Okay. So log base 3 of 7. Well, by this discussion that we just had, the b is 3, so this guy is 3, and x is 7, so this guy is 7. And the calculator doesn't allow you to choose a base other than e or 10. Okay? All right, whichever you want, either e or 10. This has to be the same as this. If you choose e, it has to be e here and e here. On a calculator, you can compute this guy, right? This is ln of 7. The calculator can do it. The calculator can do also ln of 3. And it can divide. So if you find the guy upstairs, you find the guy downstairs, you can divide the two. And once you divide the two, you found this guy, which the calculator technically doesn't give it to you. Okay, normal calculator do not give it to you. But you can actually find it via a regular or a normal calculator. Okay, because of the change of base formula. Okay. All right. Next example, show that these two are the same. Show that these two are the same. Well, this means log base 10, right? Log base 10 of e is equal to 1 over log base e of 10. This is log base e of 10. So apparently I'm going from base 10 to base e, right? I'm going from base 10 to base e. So apparently b is 10 and a is e, right? And a is e. So this would be e here and e here, correct? And b is 10, so this guy is 10. The question is, who's x? Well, the x is this e, correct? The x is this e. So this would be e then, and this is the same x, so this is the same e, right? So let's write down what we just wrote over here. Let's write it nicely. So log base 10 of e by the change of base formula, above, right? This is the same as, I'm copying, right? Log base e, so ln of e divided by log base e, which means ln of 10, right? Okay. And what's log base? What's this guy? What is this guy? ln of e. ln of e is log base e of e, right? Log base e of e. Well, log base e of e, log base a of a is this one, right? It's the 1. One of the properties we proved and we talked about before. Log base a of a is 1, so this guy is 1. So then we get 1 over ln of 10. As we wanted to show. We wanted to show that log base 10 of e, this guy, is equal to 1 over ln of 10. So we just did, right? All right. Let's go to the book. So this is technically this example. All right, I'll let you do the rest. Let me do a problem here. How about 106? use the change of base formula to write this product, log base 3 of 11 times log base 11 of 4 as a single log. Okay, so this is page this is on page 406, number 16, and 106. So we want to write log base 3 of 11 times log base 11 of 4 as a single log. All right, there are many ways to do it. The answer is unique, but there are many ways to do it. So one way to do it is, I don't know, how about rewriting each one using log base e? How about rewriting each one using log base e? Okay, so we're gonna go using the change of base. I'm gonna take each one to base e. Okay, well, the first one becomes this is one way. I'm not saying this is the only way, okay, but the answer is unique. But there are many ways to tackle this question, but this is one way. So I'm going to the change of base formula, this guy, right? Let me just erase all these things, just not to mess up ourselves. So this, all these guys, right? Okay. So we're gonna go, we said, to base, we're gonna take each one to base e. So whatever the base b is, I'm going to base e, right? So for the first one, log base 3 of 11, b is 3, x is 11. I'm gonna get log base e, as we said, I'm gonna go to base e, log base e of 11, so ln of 11, divided by log base e of 3, so ln of 3, right? So we can get ln of 11 divided by ln of 3, right? This is for the first one. For the second, still, let's go to the log base e. Let's go to the e base using the change of base formula. So b is 11 and x is 4, and a, the base I'm headed to, is e, right? So I'm gonna get log base 11 of 4 equals log base e of 4, so ln of 4, let me write it, ln of 4 over log base e of b, which is 11. So log base e is ln of 11. So I wrote each one of them in one base, in the same base, because here they are different bases, right? 3 and 11. How about we rewrite each expression in log of the same base, and we chose e. We could have chosen something else. Okay, so now look, all of these are log function acting on different numbers, but it's the same base throughout. Now we can cancel if we see at least the same thing, right? Which we do. ln of 11 and ln of 11 are the same entities. So we're multiplying by ln of 11 and dividing by ln of 11, we're done. I mean, these guys cancel each other, and then we get ln of 4 divided by ln of 3, right? ln of 4 divided by ln of 3. ln is log base e, right? Let me take you back to the question before I go this way. The question is, I want to write it as a single log. Okay. As a single log. This is not a single log. This is a quotient of logs. I want to write it as a single log. Well, contrast this expression with what we have over here. How about I actually copy it for you so kind of see it better. So how about we copy this and paste it right here. Okay, take a look at this. This is ln of 4, which means log base e of 4. Contrast it with this black part. Log base e of 4. So a is e, right? A is e, and x is 4. And this is log base e still, same base, of 3. So who's a? A is e, and who's x? 4, and who's b? Is 3, right? So that's going to be what then? That's going to be what? This one. We said b is 3, right? B is 3, and a is e, and x is 4. So b is 3, and x is what? X is the 4, right? Makes sense? So this quotient then, this purple quotient, is simply log base 3 of 4, which is a single log, obviously, right? All right, so let's take that and write it over here. This is log base 3 of 4. And this answers the question of the problem, right? The problem was write it as a single log, and we just did. All right. Okay, so this is the end of the section.